Hi everyone, I'm Sengzi. So we are now going to present the COS10004 Computing System Assignment 2 presentation. So we are from Konichiwa team, and our team includes Wang Xuanyong, Chu Sengzi, and Steven Ling. So now we are going to proceed on the introduction. So this report examines the actual and theoretical difference among several generations of programming languages, with a special emphasis on the MCUs and versus the MPUs, and a comparative comparison of Python and ARM64 assembly code implementations of the bubble sort algorithm. So the exploration commences with an analysis of the fundamental functions, architectures, and applications of the microcontrollers and microprocessors, investigating how their design impacts their technological responsibilities. So the study then shifts to a comprehensive examination of compilers, assemblers, and interpreters, elucidating the process by which scripts are converted into executable machine code. So the report focal point is the comprehensive comparisons of Python and ARM64 assembly, which exemplify third and second generation programming language. So these sections highlight the progression of programming languages and their crucial influence in developing computational solutions and improving hardware interactions. So now let's proceed to the difference between the microcontroller and the microprocessor. So microcontroller, MCU, and microprocessor, MPU, are two essential types of processor in electronics and computing, each serving unique functions and operating in separate domains. So both are critical elements of contemporary technology. However, their architecture, functioning, and fields of application differ markedly. So a microcontroller is a tiny self-sufficient system intended for embedded applications, whereas a microprocessor serves as the central processing unit of a computer and necessitates extra components to execute operations. So these sections examines the concept, components, architectures, and practical examples of microcontrollers and microprocessors, emphasizing their distinctions and applications. So by comprehending these distinctions, developers and engineers can make judicious choices when picking the suitable processing unit for particular applications, whether for embedded systems or high-performance computers. So let's move on to the definition of MCU. So according to author, a microcontroller is a processor that integrates memory and several other critical components into a single chip. It is a small integrated circuit that can work on its own and is specifically developed for monitoring and control applications. It includes key components such as CPU, memory interface, controllers, timers, and interrupt controllers, and a general purpose I/O pins to allow direction interaction with its surrounding. So microcontroller also provide bit level operation, which allow you to change specific bits inside a byte without impacting the others. So a microcontroller has three main components, which is the MPU, memory, and input-output peripherals. So memory is a critical component of a microcontroller, as it stores the data and instructions required for the operation. So microcontroller commonly use two forms of memory, which is the volatile and non-volatile memory. According to author, volatile memory, often known as RAM, the random access memory, which preserves data only when powered on the machine. So RAM is further classified into two types, which is the static RAM or dynamic RAM. So microcontroller typically use static RAM because it requires on the moderate memory capacity, while the refresh hardware required for dynamic RAM would tag valuable silicon space. The non-volatile memory, on the other hand, keeps data long after the power is turned off. So ROM was the first type of non-volatile semiconductor memory, and it has since evolved into several versions, including mass ROM, programmable read-only memory, and erasable programmable ROM, among others. So the mass ROM is the most widely used kind. And according author, the input and output peripherals are critical components that connect a microcontroller CPU and a memory to the outside world, allowing interactions between external devices. So these peripherals receive input data and send output data to the devices like sensors, displays, and communication modules. So microcontroller I/O peripherals are commonly classified as digital I/O, analog I/O, and pulse wave modulation, and communication interface including UART, SPI, and I2C. So these are the example of the microcontroller, which is the Arduino Uno, the Raspberry Pi Pico, and the ESP32 microcontroller. And now let's move on to the microprocessor, MPU. So MPU is a computer central processing unit, CPU, built on a single chip with millions of transistors linked together by sophisticated circuitry. So according to the author, a microprocessor is a type of CPU that is commonly seen in a personal computer. So it interfaces with external devices like via a data bus, which includes data and address pins as well as a few control pins. So this bus connects peripheral devices to the microprocessor, including memory, floppy controllers, USB controllers, and timers. Unlike a microprocessor cannot function independently and must be combined with other components like memory and an output device to accomplish useful functions. So a microprocessor architecture typically includes ALU, the arithmetic logic unit, a control unit, CU, registers, and a bus interface. So in any computing system, the ALU is a crucial part of the CPU which is claimed by the author. So it functions as the central processing unit's main data processing component. So computer system may have varying ALU designs and level of complexity, but all ALU have two basic components, which are the arithmetic unit and logic unit. So the logic unit operations like not, or, and others are handled. Whereas the arithmetic unit involves addition and subtraction. So the author states that the control unit, CU, is incorporated into embedded systems through the interpretations of memory commands and the guidance of other components to perform their functions. The control unit controls the flow of data within the processor. So the registers are small memory units that hold data for easy access by the processor. And bus interface provides communication between the processor and the other system components such as memory and input or output devices. And these are the examples of the microprocessor, such as the Intel Core i7, the AMD Ryzen 9, and the Apple MI Pro. So let's look at the difference between the MCU and the MPU. So in terms of architecture, the the MCU are having the Harvard architecture features, separated program and data memory, while for the microprocessor, it it is using the von Neumann architecture with shared program and data memory. So in terms of application, MCU used to perform the control tasks in embedded systems such as the appliances, and the MPUs is more suitable for difficult work on desktops and cell phones. So MCU is simpler in the instruction set, which is with a smaller instruction set for specified functions, while MPU is more complex with a diverse instruction set for various activities. So microcontroller in terms of performance is typically up to 200 MHz, which is suitable for embedded applications, while microprocessor runs faster, making it ideal for computationally heavy workloads. So MCU is cheaper due to integrated components, while microprocessor is more expensive due to the dependency on external components. And the circuit size of the MCU is more compact with integrated memory and I/O, while the MPU is larger owing to external memory and I/O requirements. So the microcontroller units, MCUs, and microprocessor units, MPUs, differ primarily in their design and function. So the MCUs, in conclusion, are having integrated component, shorter instruction sets, and are small, affordable, and well suited for control functions in embedded system. While for MPUs, on the other hand, are larger and more costly because to their more sophisticated architecture dependence on the external components and high performance computationally demanding application. So because of these differences, MPUs are more appropriate for complex computing tasks and MCUs are perfect for embedded systems. And now I'll pass the time to Stephen.
Thanks, Shengzi, and I'm Steven. Now I will be talking about compilers, assemblers, and interpreters, which form the backbone of transforming human-readable code into machine executable instructions. My sections include two main parts, which are how scripts are converted into machine code and the different generations of programming languages. Let's begin with how scripts are transformed into machine code executed by the CPU. When programmers write code, they usually use high-level programming languages like C++, Python, or Java, which are human-readable and understandable. However, computers cannot process this directly because they only understand machine code. There is a series of binary instructions like zeros and ones. Here is the overall flowchart of transforming script into machine code. The process of transforming high-level scripts into machine code involves several steps. First, programmers write the source code, which contains all the logic and instructions of the program. Once the code is complete, it undergoes compilations or interpretations, depending on the language used. For compiled language such as C or C++, the entire source code is translated into machine code at once. This process happens in stages: the lexical analysis, where the code is broken into tokens, and syntax analysis, which check the structures of the code, the semantic analysis to validate types of and variables of the code, and code optimizations, which improve performance by removing redundancy of the code. And lastly, the code generations, which produce the machine code. This machine code is then executed by the CPU. Compiled language generally offer better performance because the code is directly translated before executions. In contrast, the interpreted language like Python, Ruby are processed differently. The interpreter reads and executes the source code line by line, while this allows for easier debugging and flexibility. It comes with a trade-off in execution speed because the translation happens in real time during executions. Next, there is the role of the assembler. While modern compilers often translate high-level code directly into machine code, some language go through an additional step. The assemblers convert the low-level assembly code, which uses mnemonic representations of binary, into machine-readable instructions. This process is typically done in two passes. The first pass defines symbols and their address. The second pass generates the final project code by replacing symbolic references with their numeric values. After machine code is generated, it is linked together with other modules of library by the linker with resource reference and produces an executed program. Finally, the program is loaded into memory by the loader and the CPU executes it using the fetch, decode, execute cycle. Now, let's move to the generations of programming languages, which represents the evolutions of programming abstractions. First, the first generation's language are the most basic, consisting of pure machine code. Programmers directly write binary instructions specified to the hardware, while this gives absolute control and the fastest executions. It is highly error-prone and difficult to maintain. Next, the second generation's language. Assembly language were introduced, replacing binary instructions with mnemonics like MOV or ADD. They are easier to read and write but still hardware specific, limiting portability. Next, the third generation language marked a significant leap. There are high-level languages like C, Java, and Python. They extract hardware details, use human-readable syntax, and rely on compilers or interpreter for executions. These generations emphasize productivity and portability, enabling code to run across different hardware platforms with minimal adjustments. Next, the fourth generation's language. The fourth generation language focuses on further abstractions, enabling users to describe what they want without specifying how. Example includes SQL for database and MATLAB for numerical computations. These are domain-specific languages that prioritize simplicity and speed of particular tasks. Finally, the fifth generation language push the fifth generation language push abstractions to the highest level, focusing on problem solving and logic rather than explicit algorithms. Languages like Prolog and Mercury are used in artificial intelligence and expert systems. where the programmer defines rules and the system determines the solutions. In summary, the journey from high-level code to machine executable instructions involve compilers, interpreters, and assemblers working together to bridge the gap between human logic and the machine executions. Meanwhile, the evolutions of programming languages reflects our drive to simplify the programming while tackling increasingly complex problems. That's all for me. Now I will pass the mic to Xiong Yong.
Thank you, Stephen. Now I will demonstrate two implementations of the bubble score algorithm, one written in Python and the another in ARM64 assembly, executed on the Raspberry Pi 4. Through this, we will explore how computer programs are constructed differently across programming language generations and compare the functionality, efficiencies, and developer experience of the two approaches. Now, let's start with the Python implementation of the bubble score algorithm. The Python implementation of the bubble score algorithms use the nested loop to compare and sort adjacent elements in an array until the entry array is sorted. It prints the initial array and the array after each sort and the final sorted array. The Python allows us to focus on the logic without worrying about hardware level detail. Now, I will demo how to run the Python code. We can directly execute the Python code on our laptop. Then they will show the initial array and also show all the state of the sorting. Then they also show the sorted array after the sorting. So the output shows every step of the sort process, making Python a great language for learning and debugging algorithms. Now let's move to the ARM64 assembly implementation, which is written for the ARM's architecture for the Raspberry Pi 4. Unlike Python code, ARM64 assembly directly manipulates hardware through register and memory. Its operating must be explicitly specified, including loading data, comparing value, switching element, and even print the array. This code optimizes executes with features like early assist if no switch occurs in an interaction. Now let's move to the run the code. We need to transfer the .s file to the Raspberry Pi. Assemble and link the code using AS and the LD command. After that, we can direct call out the code. It will show out the output for the initial array, same with the Python code and the after scoring step, and also the final scored array. The ARM64 assembly code provides output only after switch focusing on significant change. This makes the output consist but require more effort to debug and understand. Now, there will simple of implementation in actions. Let's compare them and understand the fundamental difference between second generation's assembly and third generation's Python programming language. For the third generation's language like Python, address a vast hardware detail, allowing the developer to focus on algorithms and logic. In Python, this handled automatically make making it easily to write and maintain the code. However, the second generation language like assemblies are closer to machine code, requiring detailed instructions for every operation. In assembly, you manage hardware resource directly, such as a register and memory. Now move on the difference between Python code and ARC64 assembly code. Python code takes significantly less time to write and debug, while assembly requires more time and effort due to its low level nature. However, the assemblies can be more efficient in execute because it is closest to hardware, but the Python is more efficient in development time and ease of use. Python code is easy to read and understand, even for beginners. Assembly code is best code and complex, require detailed knowledge of the hardware. However, there are some similarities between the second generation language and the third generation language, such as both implementation follow the same algorithm logic with nested loop and string operation. In the end result of the bubble scorer, you can see it is the same result. In conclusions, the Python and ARC64 assembly implementation of the bubble score algorithm showcase the evolutions of programming language and the trade-off between control and abstraction. High-level language like Python prioritize ease of use, readability, and rapid development, while low-level language like assemblies prioritize control, performance, and efficiency. Thank you for watching the demonstrations and the presentation of this report.